Something is wrong with distance. Something about the universe does not add up. We are told the universe is 13.8 billion years old. We are told nothing can travel faster than light. And yet, when we look into the deepest reaches of space, we see light arriving from regions that are over 46 billion light years away. That number alone should make us pause. How can light travel farther than the age of the universe allows? How can distance grow faster than time itself? And why does the universe seem to be hiding most of itself behind limits we can never cross? Right now, at this very moment, ancient photons are reaching your eyes. They began their journey when the universe was young, dense, and unfamiliar, when the first structures were only beginning to form. But while that light was traveling, the universe did not stay still. Space itself stretched, distances expanded, galaxies drifted away, carried by the slow but relentless growth of the cosmos. By the time that ancient light finally arrived here, the place it came from was no longer where it once had been. It had been carried far beyond what intuition would ever suggest. This is the uncomfortable truth we rarely stop to consider. The universe we see is not the universe as it is. It is the universe as it was. And even more unsettling, most of the universe may already be lost to us forever. There exists a boundary around us, not a wall, not an edge you could ever touch, but a limit defined by time, light, and expansion. A horizon beyond which information can never reach us, no matter how advanced our technology becomes, no matter how long we wait. We live inside a growing bubble of visibility, a cosmic island surrounded by an ocean we will never explore. And the strangest part is this: that boundary is not fixed. Some parts of the universe are slowly slipping away from us right now. Galaxies are crossing invisible lines, fading from reach, their future forever disconnected from ours. So what exactly is this boundary? Why is it so much farther than the age of the universe suggests? And how is it possible that the universe can be both finite in what we see and potentially infinite beyond? To understand this, we must first confront the most misunderstood concept in modern cosmology: the observable universe. At first glance, the idea seems simple. The universe is 13.8 billion years old. Light travels at a fixed speed, so you might expect the farthest thing we could possibly see to be 13.8 billion light years away. But that intuition is wrong, very wrong. The observable universe is not a sphere with a radius of 13.8 billion light years. It is nearly 3.5 times larger. Its radius today is about 46 billion light years. This is not a trick of measurement. It is not an error in our instruments. It is a direct consequence of how space itself behaves. Here is the crucial detail most explanations skip. Light moves through space, but space itself is not static. While photons travel at a constant speed, the fabric of the universe stretches beneath them. Distances grow while light is still in transit. Imagine a photon leaving a distant galaxy when the universe was young. At that moment, the galaxy might have been only a few billion light years away. But as the photon moves forward, space expands behind it. The destination retreats. The path lengthens. The finish line keeps moving. By the time that photon finally arrives here, the galaxy that emitted it is no longer a few billion light years away. It is tens of billions of light years distant. This is why the observable universe is so vast. Not because light traveled faster, but because the universe expanded while the light was en route. And this leads to a deeply unsettling realization. There are regions of space we can see, but can never reach. No spacecraft, no probe, no future technology will ever cross those distances. Even if we could travel at the speed of light, the universe would carry those destinations away faster than we could chase them. We are not looking at distant places. We are looking at ancient moments. Every galaxy you see is a memory. Every deep space image is a fossil. And the farther you look, the deeper into the past you are forced to stare. This is why the observable universe is not a map of reality as it exists now. It is a historical archive, incomplete, biased, and slowly changing. The boundary of this archive is called the observable horizon. It marks the greatest distance from which light has had enough time to reach us since the beginning of the universe. Everything beyond it may exist. It may contain galaxies, stars, and structures just as rich as our own region. But it is forever hidden. No signal from those regions has ever reached us, and none ever will, not because of distance alone, but because of time. Here is the uncomfortable question that follows. If most of the universe lies beyond what we can ever observe, how confident can we really be about the universe as a whole? Are our cosmological laws universal, or are they local descriptions of a much larger reality we will never access? We often speak as if the observable universe is the universe. But it isn't. It is only the part that had enough time to reveal itself. And even that window is deceptive. Because while the observable horizon slowly expands, another boundary is quietly closing in, one that determines not what we can see now, but what we will ever be able to see. And this next horizon is far closer than most people realize. Space is stretching while light is traveling. To truly understand why the universe appears so much larger than its age suggests, we need to let go of a deeply ingrained idea. We tend to imagine space as an empty, motionless stage, a fixed arena where objects move through it. But space is not a passive background. Space is active, dynamic, and relentlessly stretching. When light travels across the universe, it is not moving through a static void. It is moving through a fabric that is expanding in every direction, at every moment. A useful way to picture this is not as a race, but as a struggle. Imagine a photon, a single particle of light, leaving a distant galaxy shortly after the universe becomes transparent. It begins its journey toward us at the fastest speed anything can possibly move. But the path it must cross is changing. As the photon advances, new space continuously forms between it and its destination. The universe adds distance faster, the farther apart two regions already are. So the photon is not simply traveling across space. It is fighting against it. This is why a simple calculation, speed of light multiplied by age of the universe, fails so dramatically. It assumes the distance is fixed. The universe behaves less like a rigid road and more like a moving walkway, one that accelerates as you move farther along it. For nearby regions, the expansion is gentle. For distant regions, it becomes overwhelming. And this leads to a counterintuitive truth. Some of the light we see today was emitted by galaxies that were already receding from us faster than the speed of light. That statement alone sounds like a violation of physics. But it isn't. Nothing locally moved faster than light. No galaxy broke the cosmic speed limit. Instead, the space between us and those galaxies expanded faster than light. This distinction is crucial. The laws of physics limit how fast objects can move through space. They place no limit on how fast space itself can expand. And on the largest scales, it does. Right now, there are galaxies whose recession speed, driven entirely by cosmic expansion, exceeds the speed of light. Not because they are flying away like rockets, but because the space between us and them is stretching at an extreme rate. And here is where things become deeply unsettling. Some of those galaxies are still visible to us. We are receiving light they emitted billions of years ago, when they were closer, when the expansion between us was weaker. But if those galaxies were to emit light today, that light would never reach us. It would be dragged backward by the expansion of space, losing ground faster than it could advance. In other words, we are seeing galaxies that are already causally disconnected from us. We are observing their past, but their present and future are forever inaccessible. This raises an uncomfortable question. If the universe allows regions to become permanently unreachable, even while remaining visible for billions of years, at what point does seeing something stop meaning it is part of our universe in any practical sense? Is a galaxy still part of our cosmos if no signal it sends now can ever reach us? Or are we simply watching ghosts, images frozen in time, slowly fading as the universe pulls us apart? The expansion of space does not just increase distances. It reshapes causality. It decides which events can influence us and which are lost forever. And in the earliest moments of cosmic history, this expansion was not gentle at all. It was violent, extreme. And it permanently altered what we would one day be able to observe. To understand why the universe looks the way it does today, smooth, vast, and strangely uniform, we must return to a moment when space itself expanded faster than anything we can currently imagine. A moment known as cosmic inflation. Inflation changed everything. To understand why the universe looks the way it does today, we need to return to a moment so brief that it barely qualifies as time at all. A fraction of a second after the universe began, something extraordinary happened. Space didn't just expand, it exploded outward. This phase is known as cosmic inflation, a period when the universe grew faster than light, faster than intuition, faster than anything we observe today. In less than a heartbeat, regions of space that were once unimaginably close were torn apart and flung across enormous distances. And this matters more than it sounds. Because inflation didn't just make the universe bigger, it set the limits of what we can ever observe. Tiny quantum fluctuations, microscopic variations in density, were stretched to cosmic scales. These ripples became the seeds of galaxies, clusters, and the large-scale structure of the universe. But inflation also created a permanent separation. Some regions were pushed so far away so quickly that no signal from them could ever catch up to us. Not then, not now, not ever. Those regions may still exist. They may look very much like our own, but they were effectively erased from our observable reality almost at birth. This leads to a deeply unsettling idea. The universe may be vastly larger than the part we can see, not just in space, but in history. There may be regions that evolved entirely beyond our causal reach from the very beginning. Different initial conditions, different cosmic histories, possibly even different physical outcomes. And we would never know. Everything we call the universe is shaped by a brief, violent event that lasted less than a second, yet determined the fate of visibility for all time. But even inflation did not create the final boundary. Another limit emerged later, quieter, slower, but far more cruel. A boundary that decides not what we can see now, but what we will never be able to see, no matter how long we wait. The cosmic event horizon. There are two different edges to the universe, and confusing them changes everything. The first is the observable horizon, the boundary of what we can see today. The second is far more disturbing. It is called the cosmic event horizon. This horizon marks the maximum distance from which light emitted now or in the future will ever reach us. And it is much closer than the edge of the observable universe, roughly 16 to 18 billion light years away. Beyond this distance, galaxies are not just far, they are lost. Even if they shine forever, even if the universe lasts eternally, no new information from them will ever arrive here. Their future is causally disconnected from ours. We may still see their ancient light today, light emitted billions of years ago when they were closer, but their present is already beyond reach. This creates one of the strangest illusions in cosmology. We can observe galaxies that no longer exist for us in any meaningful sense. From our perspective, they slowly fade. Their light stretches toward redder wavelengths. Time appears to slow for them. Their evolution seems to freeze. Eventually, the last photons arrive. And then, silence. Those galaxies do not explode. They do not vanish dramatically. They simply slip beyond the horizon, leaving behind only an image of what they once were. From their perspective, the same thing happens to us. They would see our galaxy slow, redden, and fade. No warning, no final signal, just permanent separation. This is not science fiction. It is the measured, predicted future of an accelerating universe. And it raises an uncomfortable final question, one that has nothing to do with equations. If the universe is steadily isolating every region from every other, if visibility is shrinking, not expanding, then are we living at a special moment? A brief window when the universe is still visible, connected, and understandable? Or are we already too late to see most of what truly exists? The edge of the universe is not a wall in space. It is a boundary in time, causality, and information. We are not trapped by distance alone. We are limited by the history of expansion itself. The universe may be vast, beyond imagination, but only a fraction of it will ever be part of our story. Everything else is already slipping away. So the real question is not how big the universe is. The question is this: how much of reality have we already lost without ever knowing it was there? And if the universe continues to accelerate, what will future civilizations believe the universe is once almost everything has disappeared from view?